So if I gave you this one, pennies minted after 1982 are made from 97.5% zinc and 2.5% copper. Following data gives the weight in grams of 17 randomly selected pennies minted after 1982. Treat the data as a simple random sample. Estimate the population mean weight of the pennies minted after 1982. So what am I asking you to find? The mean weight. How do we find the mean? Add them up and divide by the number, which I told you was 17. So my sample is 2.464 grams. If I picked another 17 pennies, would I get the same mean again? Probably not. Kind of like we talked about yesterday. Every time I take a different sample, I'm probably getting a different proportion. So we know just saying the average weight is 4.64 grams is probably not right. So if we want to be more accurate, we have to give a range of values. We have to say it's going to be between these numbers. This involves a new distribution. We've been using the normal distribution for a long time, and this one is a little bit different. It involves what's called the student's T distribution. So if you have a simple random sample of size n from a population, if the population is normal, then we can have a distribution of T values, where x bar is the sample mean, s is the sample standard deviation. Other variables in here, n would be the number in our sample. What would mu represent? What is mu? The mean of the population. X bar is the mean of our sample. Mu is the mean of the population. So just like everything else, this is on your formula sheet. So that means instead of calculating like z-scores, we're dealing with t values. And the reason is because our sample, especially if we're not dealing with a large sample, may not strictly be normal. And so it turns out to have a slightly different distribution. Some properties with this, it changes based off degrees of freedom. Degrees of freedom, we had this like way back in the very first unit when we talked about standard deviation. Degrees of freedom is n minus 1. Basically, this is a distribution that calculates probabilities for different sample sizes. And it turns out if as the n gets bigger, it turns into a more normal distribution, which we've kind of already said, the bigger our sample, the more normal it becomes. But when n is small, it's not strictly normal, so that's why we're using this t distribution. It is similar to the normal, so it's centered at 0, half the area above, half the area below. It's just flattening out, getting closer to 0. So number 5 is just kind of explaining the difference between this and the normal. The area in the tails is a little bit more than in our standard normal distribution. So if you think about like empirical rule, it tells you 95% falls within 2 standard deviations. There's going to be more on the ends. less within the first few standard deviations on this. So it's a little bit flatter than our regular normal, but when our sample gets bigger, it becomes more normal. So this is kind of the shape, and the blue one is showing you the regular normal curve. This pink one is with a sample of 15, orange is a sample of 5. So we can see the orange one is our small sample, and it has less in the middle and more on the ends. As my end gets bigger, it's getting closer to the normal. So they are very, very similar, but slightly different. So you will notice that on the back of the page with your normal distribution, we have another table for the T distribution. So that is the one that we actually have to use with this. Now, unfortunately, the notation is a little bit different than with the normal. So on the normal table, we know this number gives us the area to the left. If you look at the picture on the T distribution, it's giving you area to the right. Okay. T equals 0 would be the middle. You'll notice then you have two different options. Going down, those are the degrees of freedom. Do I have every possible degree of freedom here? No, so we are more limited with this table. We can't do everything on this table. We could have a more extensive one, but we'll also talk about using our calculator to help. And then the numbers across the top of this table, 0.25, 0.2, so forth, those are actually your probabilities or your areas. So they flipped it. The number inside the table is the T value, which would be like the thing down here. The number at the top is your area, which is that light blue shaded part. So it is reversed from how the normal table is set up. Do you guys understand what I'm saying? So let's practice trying to use this table. If I want to find the T value such that the area under the T distribution to the right of the T is 0.2, assuming 10 degrees of freedom. Right, so what that means, T distribution, this area is 0.2, and you have to find out what T is. Notation you might see is like a T with the subscript of 0.2, 10 degrees of freedom. So we go down the degrees of freedom to 10. We go over until the probability at the top is 0.2. And what is our T value? What if I wanted, could you tell me what the T would be on this side so that this area was 0.2? Negative 0.879, because it's symmetric, it's centered at 0. The table doesn't give us the negative values, it just kind of assumes that you understand that if you were looking for that end, it would be that. So. Alright, let's try another one. So I want the T, so the area under our distribution, but to the right, so right here, is 0.1. We have 15 degrees of freedom. So 15 degrees of freedom, go over to 0.1, what is our T? Any questions about that? So now let's talk about how to make a confidence interval with this. If I want my confidence interval, we have to have simple random data. Sample size has to be less than 5% of total population. The original data has to either be normal or very large. So those are kind of some stipulations here. We're not going to focus on that too much right now. We will continue to use this T distribution in the next chapter, and we'll hit that a lot harder then. So just like yesterday when we were doing our or our confidence interval for p hat, it was p hat plus or minus your margin of error, and we had that formula for calculating it. That's what this is, except it's centered around x bar. So again, all on your formula sheet. Second bullet under chapter 9. So it's x bar, the sample mean, plus or minus t alpha over 2 times s over the square root of it. S would be the sample standard deviation. Alpha is going to be our confidence level. So very similar to yesterday, except we had to use the normal table with our z. Here we're looking for our t. So let's try setting one up. This data shows reported miles per gallon of 2011 Ford Focus automobiles for 16 different owners. Treat the sample as a simple random sample of all 2011 Ford Focus automobiles. Construct a 95% confidence interval for the mean miles per gallon. Alright, so our formula for the confidence interval is x bar plus or minus t alpha over 2 times s over the square root of it. Alright, I know my n, it's 16, but do I know my sample mean or my sample standard deviation? No. Sample mean isn't too hard to calculate, but standard deviation is a little bit lengthy. Do you guys remember how we can get the calculator to give us those values? The stat, edit, and we're going to put all of our data in L1. All right. So then if we go to stat, calculate one variable statistics, our list should be L1. Frequency, make sure there is nothing in your frequency list, or a 1 at the very least. All right, so now we can see our sample mean is 36.8, sample standard deviation 2.917. What was the last digit? 9171. We got 4 decimal places. All right. Now we need the T alpha over 2. So if we are doing 95%, that means 95% is in the middle. So we have 5% left over, so how much would be on each side? Mm-hmm. 0.05 divided by 2, so 0.025. So we need to look up T of 0.025. How many degrees of freedom do we have? N is 16, and I said degrees of freedom is n minus 1, so 1 less. So we have 15 degrees of freedom. T is 0.025. So go to your table. So T value is 2.131. So then we can do our calculation. Our mean, 36.8, plus and minus our T, 2.131, times S, 2.9171, over the square root of n. Okay. So what does that mean? We got our confidence interval. So if I ask you to write a sentence telling me what that means, what would we say? Don't forget to include your confidence level. So we are 95% confident. The mean, I'll put it on, is between 35.2459 and 38.354. All right. Now, we can also do this on our calculator. So I wanted to show you guys how to do that. Let's just do this one on the calculator first. So on your calculator, you are going to go to Stat, Test, number 8. So we are looking for, I know it's kind of confusing because number 7 is the z interval, and that's not what we did yesterday when we were looking at our z values. Remember, we had to go down to a, the 1 proportion z interval. But right now we are doing what's called a t interval, so number 8. So then you have to tell your calculator, are you basing it off data or stats? So data is like when we had that list of numbers and we put it in our L1. Stats would be if, I didn't tell you the original numbers, but in the problem I just said the sample had this for the mean and this for the standard deviation. So if it's set on stats, it's going to ask you for the mean, standard deviation, and the n. If you flip it over to data, it asks you what list it's in. So make sure that says L1 because we've already entered it there. You need a confidence level, so this is 0.995. And so then when you calculate, so stats, that's number 8. And we have data, 95. So when you run it, we get this far. Is that pretty close to what we had? Yeah, so you can see sometimes there's a slight variation just because the t values we're using on our table are very limited. So the calculator most of the time will be more accurate unless we have one of the common probabilities on our table. Alright, let's try another one. This one, same question, but I'm asking you to do a 99% confidence interval. So let's do it both by hand and on the calculator and compare. The mean is the same, right? We had the same, what was our mean on the last one? Oh, sorry, this is not the same one. This is our pennies example. We didn't do that whole thing.
Yeah.
We just did the mean. We didn't find the standard deviation. Alright, let's enter this one in so we can get the mean and standard deviation from our calculator. Right, so when you do that, what does it tell us our mean is? 2.464, is that the same thing we did when we calculated by adding up and dividing by 17? Yeah, so we're not getting different answers, just different methods. I gave you a standard deviation in the problem, 0.02. Is that the same as the standard deviation on your calculator? Yeah. Oh, sorry, I did not. I gave you the mean of the population. My goodness, I need to quit trying to think about two things at once. Alright, so if I'm going to do this confidence interval we can use our calculator. We can also do it by hand. Let's do the calculator first and see what we get. So how do we do this? Stat test 8. Is this one based on data or stats? Okay. List is L1. Confidence level is? Okay. And we get what? So that means we are 99% confident the population mean weight is between those two. So we're using this interval for my sample to guess a weight of the entire population. If I were going to do this by hand, the formula is x bar plus or minus what? Times. Okay. So we got our x bar. Okay, T alpha over 2. Okay, so if we have 99% in the middle, that only leaves 1% for the ends. We have to divide by 2, so then it's 0.005. How many degrees of freedom do we have? So if you go to your table, 0.005, 16 degrees of freedom, our T is 2.921. Times S, what was our sample standard deviation when we had our one variable statistics? We're looking for the S, not the sigma, so 0.0177 divided by the square root of n. This isn't degrees of freedom, this is the number in our sample, which was 16. So let's see if we get the same thing.
I thought it would be 17.
Yep. I just said it wasn't the degrees of freedom, and then I wrote my degrees of freedom, didn't I?
Where do we get 0.0177?
The one variable statistics, the sample standard deviation. So when we put the data in our calculator at the beginning, you can go to stats, calc, one variable statistics.
we look at that.
Mm-hmm. So is this exactly the same as our calculator?
No, it's
Pretty close. The reason it's different is our standard deviation, we rounded 4 decimal places. If we kept all of them, it would have been more accurate. So just make sure, because depending on whether you do it by hand or from the calculator, your final digits may be a little bit different. Make sure you're showing me enough work that I know how you got what you were doing. The last thing we did yesterday, we did confidence intervals for the p-hat. So we just did that for x bar. Then we talked about how big our sample needed to be for the p-hat. So we want to do the same thing with x bar. So again, this is on your formula sheet. To figure out how big your sample needs to be, we have to use this formula. Now, it goes back to z's instead of t's, just to make things fun. But that has to do with the fact that the original population is normal. So we go back to the z's here. S is sample standard deviation. E is the error, which remember, error is the thing we're adding or subtracting. So this represents error. A lot of times though in these problems I'm going to give you a percent error. So I'll tell you what that number is and you just have to plug it in. So if I look at this one. So if I wanted to go back to my car problem and estimating miles per gallon, how big would my sample need to be to estimate the mean miles per gallon within half a mile per gallon with 95% confidence? So my formula. N is Z alpha over 2 times S divided by E squared. So I have to find these things. All right, Z alpha over 2. If we are 95% confident, that means 95% is in the middle. So 5% split 2 ways, so each one gets 0.025. Right, so we need the Z that matches that. Now remember, this one, some of them are given at the bottom. If not, then we have to look at, we're essentially finding, this would be 0.975, so you'd be looking inside your table to find the closest area to 0.975 that we could. And we get a 1.96, which this was one that told us at the bottom. The sample standard deviation, we did that in example 4, right? We found our sample standard deviation there to be 2.9171. So we got that from the previous example. How much error are we allowing for? .5. I have to be within half mile. Yeah, so E is 0.5. So N is 1.96 times 2.9171 divided by 0.5 squared. This is another one where if you round a little bit, it will change your answer. You know, if I rounded my standard deviation to only 2 decimal places, I would have got a different N. So make sure you're showing me what you're doing. So what would I have to say? How many would we need in our sample? Yeah, we always have to go up here. So we would need at least 131 in the sample to make sure that our sample our window was within a half mile per gallon of the true value. Other questions? We have quite a bit of time left. guys have that packet, you're probably still working on yesterday's portion, which is fine. On Tuesday, when we get back, I'm going to do a little bit of review with you and we'll have some time to finish up that packet as well, so it's not due until Wednesday. So, you'll have some